And recording has started, so let's jump in. Yikes! This is a big chapter. Any thoughts or comments before I jump into this? I know I had a lot of fun. There's some fun math that I'm hopefully got examples in, and we'll just go ahead and get started here. So in this chapter, we're going to be covering rectangular and polar coordinates, complex numbers, electric, magnetic, and electromagnetic fields, time constants, impedance and admittance, reactive power and power factor, resonant circuits, Q and bandwidth, inductors with magnetic cores, 3 subsections, 71 questions, and 38 pages. And I forgot how many, I didn't put it in there, of videos and time and all of that fun stuff, but hopefully that's been covered. So our first area is RC and RL time constants, and there's 3 questions. And I need to move this over so I could read the screen.
62.
Okay. Hang on real quick. Got another pop-up. Okay. Sorry about that. First question. What is the term for the time required for the capacitor in an RC circuit to be charged to 63.2% of the applied voltage or to discharge to 36.8% of its initial voltage? A, an exponential rate of 1. B, one time constant. C, one exponential period. D, a time factor of 1.
Bravo.
B.
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 B is correct. What is the time constant of a circuit having two 220 microfarad capacitors and two 1 megohm resistors, all in parallel? A, 55 seconds. B, 110 seconds. C, 440 seconds. Or D, 220 seconds.
Delta.
B.
Dog.
Delta is the correct answer, and I stuck some fun math in there. So first thing,
Jim, question for you.
Yeah.
When you get questions like this, is it worth trying to really understand the theory for the passing the test, or is it just better to understand when you see this is the answer?
So that's a really good, that's the question of
We
the
don't have
night.
that kind of time. Yeah. Mm-hmm.
Yeah. So my first answer when I was just, so let me ask you this. What's the goal? Is the goal to pass the test, or is the goal to understand and pass the test?
Pass the test.
Okay.
Well, understand and pass, but there's certain things that are
Pass the
so
test.
above my pay grade that, like with this one, I like memorized 220, good, done.
Yeah.
And not to diminish all the stuff that we've learned or the stuff we'll continue to learn, but is this one of those that are like, okay,
Yeah.
I think it's important to pass the test, but it's very important to go back and really understand
learn and
what's
understand
going on.
it. Yeah. And I'll be straight on with you. My goal was to pass the test because at the time that I was taking things, I said, oh, I want to be like Johnny on the spot and just pass the test. So I did just I memorized all of the answers. And now, 6 years later, I'm saying, let's go back and really try to understand what was going on. Because some of this math that's involved in this section, this chapter, I haven't done since 1978. It's just like, holy smokes, this is like, try to dig the, dust off the memory banks. But yeah, so that's, if the goal is to just pass the test, just memorize the answer.
Jim, we had a guy last week that said, that it's important to get the license, but then you learn by doing. So,
Yes.
when I got my general, I learned so much. I mean, it's not like I knew everything once I got the general. So I'm going to learn a lot more when I have this next step, I believe. So.
Yeah.
From a practical standpoint, when will you use this if you had to use this from practically in the future?
Well, a good example would be discharging a power supply. If you had a linear amplifier and it had 2,000 volts on it, they have a bleeder resistor across it. When you turn off your amp, right, there's resistors, there's capacitors. So it could be a matter of life and death. These equations aren't real hard at all. If you look at the bottom of page 410, RC constant is simply R times C. So the only thing that I think is scaring people here is the units, right? So mega ohms, microfarads, millifarads. I think if you just got your head around that and understand that RC is equal R times C, it's pretty easy, I think. I'm just curious with the team here, where's the apprehension to something like this? Is it the units or the equation?
Well, since I brought it up, I'll tell you, I just don't have the use for it right now. So understanding it, knowing that there's 3 questions, for me to sit back and really understand this theory, and I understand the application of it. I got an amp and a power supply, I get it. But to understand the absolute specifics of it is just going to take me more time than to know that, all right, I've got 3 questions, I've got to pass 35 of them, and where does this one fall?
R times C. So basically you get your resistor in the ohms and your capacitor in the farads, and that's what they're showing there. So it's just a simple multiplication. But okay, that's my 2 cents.
Yeah, it's also the number of equations related to this subject area.
Well, we only got into one. We're only at 1 so far.
That's right.
So for me, trying to memorize this stuff right now is totally useless, or trying to learn this stuff right now is useless because I'm not going to apply it probably for some time. And if I try to learn it now, I will forget it and have absolutely no comprehension of it until when I need it. So I learn better executing rather than just reading about it or trying to be taught it. I have to actually execute on it in order to actually learn and retain it. So my goal here is to simply pass the test, because once I've got the license and I can actually start doing some of this more advanced stuff, then I'll start actually applying this stuff, and then I will retain it because I'll need to. But I'm not going to, the way my brain works is I can learn things with no problem, but if I don't use them, they will disappear quickly and I will never be able to recall them. I will have to learn it again. So for me to learn it now is a complete waste of time because I won't be applying it probably for 1 or more years away.
So I have a rhetorical question, and please don't think I'm being a smartass here, but why are you taking this extra class if you don't want to learn the material? It's just an honest question. I don't mean that to sound brash.
It's not that I don't want to learn the material. Learning it right now is not going to do me any good because I will forget it.
Okay. Well, that's not. This is Daniel. This is Daniel, KO7WM. That's not a problem. My sister said this. College taught her where to look, and what this course is going to show you. You may not remember the actual formula, but you'll know someone who does and know where to find it if it does. The big thing here is when you turn off an amplifier with a power supply, don't put your hand in there right away because time constant, those capacitors are being bled off slowly.
I've discharged the capacitor.
Don't put your hand in there right away. Let it calm down. Give it sometimes even a half hour or more on the high power. If you're getting like a linear, which you're doing at 1500 watts, full can, turn it off. If you have to open it up and look at it, keep your hands out of there for a half hour or so. That's what that's the basic thing behind it. And this formula will tell you how long you have to keep your hand out of there.
Yeah.
Thank you, Daniel.
To back up what Daniel just said about, college taught his, you said it's your sister, where to look?
Yeah, my sister, yes, in college.
20 plus years in the IT industry taught me the exact same thing. Don't memorize anything because it's totally useless to do so because it expires in 2 years. Learn where to look the crap up and move on. because you're not going to be able, if you had to memorize and keep all the knowledge that you have to learn to do your job, you would never be able to retain it all. And it changes so quickly, it's useless to try to do so. You memorize the stuff that's basics and is constant and never changes, but the other stuff, the high-end technology, don't bother learning it, just know where to look it up because it's always going to change.
Fair enough, but these aren't Maxwell's equations. These are basic electronic questions, but anyway.
Yeah, you study and how you retain things. That's fine. In this
Right.
case, I'm going to say memorize it for the test and know that it's out there and look it up when you need it.
Yep. And then for those that are looking for the actual, I'm trying to get all of the numbers and the formulas and stuff, just for those that are wanting to go down that other path. So both sides, good stuff. In what direction is the magnetic field oriented about a conductor in relation to the direction of the electron flow? A, in the same direction as the current. B, in the same direction opposite to the current. C, in all directions omnidirectional. Or D, in a circle around the conductor.
D.
D.
Delta is correct. Now we're going to move into phase angle, just 2 questions on this one. Eli, the Iceman. Oops, I gave the answer. What is the relationship between the AC current through a capacitor and the voltage across a capacitor? A, voltage and current are in phase. B, voltage and current are 180 degrees out of phase. C, voltage leads current by 90 degrees. Or D, current leads the voltage by 90 degrees.
Delta.
Delta is correct.
Yeah.
Eli the Iceman. So in a capacitive, I leads the voltage. What is the relationship between the AC current through an inductor and the voltage across an inductor? A, voltage leads current by 90 degrees. B, current leads the voltage by 90 degrees. C, voltage and current are 180 degrees out of phase. Or D, voltage and current are in phase.
A.
A is correct, and that is the Eli in Eli the Iceman. Complex impedance. We have 9 questions. Which of the following represents a capacitive reactance in rectangular notation? A, negative JX. B, positive JX. C, delta. D, omega.
E.
Alpha.
Alpha is the correct answer for capacitive reactance in rectangular notation is minus JX.
When we get into the rectangular chart, the graph, you're going to see at the lower right quadrant is the capacitive. The upper right quadrant is going to be the inductor. So the inductor is positive and the capacitor is negative.
Daniel, can you also remind me to bring up your slide when I have your slides here, but I don't remember where.
Okay, when we get into the rectangular coordinates problems, let's play those six PowerPoint thing right away, and I'll show you the 4 triangles and the positive negatives at that.
Okay,
we'll go through
gotcha.
that point.
I pulled it up on my other computer so I could see it because I'm presenting on this one and I have it ready, but I forgot where it was. Okay.
Yeah.
Okay, moving on with this one. How are impedances described in polar coordinates? A, by X and R values. B, by real and imaginary parts. C, by phase angle and magnitude. Or D, by Y and G values.
C.
Charlie.
Charlie.
Charlie is correct, by the phase angle and the magnitude. Which of the following represents an inductive reactance in polar coordinates? A, a positive magnitude. B, a negative magnitude. C, a positive phase angle. Or D, a negative phase angle.
Charlie again.
D.
Inductive reactance in polar is C, a positive phase angle.
Yeah.
What coordinate system is often used to display the resistive, inductive, and/or capacitive reactance components of an impedance? A, Maidenhead grid. B, Faraday grid. C, grid. Or D, rectangular coordinates.
D.
Delta.
Delta is correct, rectangular coordinates. What is the name of the diagram used to show the phase relationship between impedances at a given frequency? A, a Venn diagram. B, near field diagram. C, phasor diagram. Or D, far field diagram.
Charlie.
Charlie.
Charlie is correct, the phasor diagram. What does the impedance 50 minus J25 represent? A, 50 ohms resistive in series with 25 ohms inductive reactance. B, 50 ohms resistance in series with 25 ohms capacitive reactance. C, 25 ohms resistance in series with 50 ohms inductive reactance. Or D, 25 ohms resistance in series with 50 ohms capacitive reactance.
Bravo.
B.
Bravo is the
B.
correct answer. 50 ohms resistance in series with 25 ohms capacitive. If it was plus 25, it would be A, 25 ohms in inductive. But in this one, it is B.
And Jim, on some of these questions, you can immediately eliminate like two of the answers right off the bat, and then you've got like a choice of giving you a 50-50 chance on the question. Because like with this one, C and D, 25 ohms, it's like we know that it's not there.
Yep.
And so then you only have to remember, okay, minus is capacitive, and yeah.
Correct. Yep. Yep. Those distractors, they like to flip the numbers and try to get you off tangent. Okay. Where is the impedance of a pure resistive plotted on a rectangular coordinates? A, on the vertical axis. B, on a line through the origin slanted at 45 degrees. C, on a horizontal line offset vertically above the horizontal axis. Or D, on the horizontal axis.
Delta.
D.
D, delta on the horizontal axis is correct.
When you see the rectangular coordinates chart graph, it'll make me be very plain. That's that one that in the center that goes horizontal.
Okay. What coordinate system is often used to display the phase angle of a circuit containing resistance, inductive, and/or capacitive reactance? A. Maidenhead grid. B. Faraday grid. C. Elliptical coordinates. Or D. Polar coordinates.
Polar coordinate
Delta.
T.
Delta
Yeah,
is correct.
It's either going to be the rectangular coordinates or the polar coordinates. Both will do that. In this case, polar is the only answer. This here.
When using rectangular coordinates to graph the impedance of a circuit, what do the axes represent? A. The x-axis represent the resistive component and the y-axis represents the reactive component. B. The x-axis represents the reactive component and the y-axis represents the resistive component. C. The x-axis represents the phase angle and the y-axis represents the magnitude. Or D. The x-axis represents the magnitude and the y-axis represents the phase angle.
D.
Delta.
A.
Oh, whoa.
Alpha is the correct. In a rectangular coordinates, the x-axis is the resistive. X-axis is this one. And the y-axis is the reactive component. And that is on page 4-16. Okay. Now we're going to move on to admittance and susceptance. 11 questions. What letter is commonly used to represent susceptance? A, the letter G, B, the letter X, C, the letter Y, or D, the letter B?
Delta.
Delta.
Delta, the letter B. Letters representing letters. Okay. How is impedance in polar form converted to an equivalent admittance? A, take the angle and change the sign of the magnitude. B, take the reciprocal of the magnitude and change the sign of the angle. C, take the square root of the magnitude and add 180 degrees to the angle. Or D, square the magnitude and subtract 90 degrees from the angle. The answer in this one is B, changing impedance to admittance. You take the reciprocal of the magnitude and change the sign of the angle. That's on 422. What happens to the magnitude of a pure reactance when it is converted into susceptance? A, it is unchanged. B, the sign is reversed. C, it is shifted by 90 degrees. Or D, it becomes the reciprocal.
D.
Delta is correct. It becomes the reciprocal. What is susceptance? A, the magnetic impedance of a circuit. B, the ratio of magnetic field to electric field. C, the imaginary part of admittance. D, the measure of efficiency of a transformer.
C.
Charlie.
Charlie is the correct answer in this one. The imaginary part of the admittance. Hang on real quick. Okay. What is the phase angle between the voltage across and the current through a series RLC circuit if the XC is 500 ohms, R is 1 kiloohm, and XL is 250 ohms. A, 68.2 degrees with the voltage leading the current. B, 14.0 degrees with the voltage leading the current. C, 14 degrees with the voltage lagging the current. D, 68.2 degrees with the voltage lagging the current.
Okay, Jim, let's stop right here. You got the XL of 250 ohms minus the XC of 500 ohms gives you a minus 250 ohms. Is that a negative or a positive?
Negative.
It's a negative, so it's capacitive circuit. So therefore the voltage is going to lead. So now you got A or B.
B.
And you got a kilo ohm versus 250. That's going to be a 14-degree angle. So it's going to be B. At this point, we can go ahead and play those slides if you want to bring them up.
Okay. Let me stop.
What they've done on this last change here with the extra pool, they've dropped a lot of these questions like this and got more word questions, which I really like because it helps to explain it. But if we get those PowerPoints up,
Okay.
we'll walk through it real carefully. And those PowerPoints have helped a lot of students answer these things quickly without doing the math in. But it's the XL minus the XC gives you your net X component. And that's positive would be inductive and negative would be capacitive.
That
Okay.
was the answer C.
Yeah,
The
hang on.
answer is C.
Yeah.
Yeah,
voltage
we're
lagging
gonna
current.
come back to that. Okay, so this one, Daniel, right? Yeah.
Okay.
Sorry about that.
Okay. So we're looking at the 14-degree.
Yeah.
Right.
Yeah. 14 degrees is the phase angle. Yeah.
I don't see the chart on my,
He hasn't
Oh,
shared it
sorry.
yet. You haven't shared it yet, Jim.
Yeah, I'm sitting here pulling it up going,
You can see it. Everybody else can. Yeah.
Okay, share the screen. There we go.
Okay, there it is. You see the upper left triangles, 14 degrees. You go, in this case, you do go 1,000 horizontally and then 250 up. This triangle will be reversed. We'll see that in one of the later slides. This is the inductive slide, and the counterpart would be the one going down. That's 14 degrees. You got a 45 degrees where it's 100 and 100, gives you 141 ohms of impedance. Then you've got the 37, which is as a 3-4-5 triangle. 300 up, 400 horizontal, and 500 across the hypotenuse. And then they got the 53 angle triangle, which is 300, 400 up, and 500 across the. Those are the four triangles you're going to see on the rectangular coordinates. Go to the next slide, Jim. Okay. Now this is Pythagorean theorem. A squared plus B squared equals C squared. Next slide.
What was those two?
You didn't bring the, okay, you didn't get the whole thing then. Okay.
Do you have them handy there?
I am in the field. I was still
sorry.
working when you started the class, so I can't get it to you. I didn't save evidently when I pulled that up.
Yeah, it was just those two.
Yeah, okay. We'll go back to your slides in there. Yep, you didn't get the whole thing. So.
Oh, shucks.
well, Daniel, where did you find those triangle charts?
I made them for the extra class.
Okay, and how did you design them? I don't mean
I designed them from the questions. Those are the same questions that are on the general radio operator license test, and they're also on the extra test. So those they're used for both persons, the commercial license as well as the extra license. And so after teaching it for 3 or 4 years, I designed those slides from the questions that have it. Those are those are the 4 angles you're going to see in the questions.
Okay. Now I need to.
Can we get a copy of that?
Yeah, when I get the updated slide deck, we'll send that out to you.
Great.
I just happen to be in Bothell right now, and Kirkland right now, and I live in East Hill, Kent, so I'm not at my computer. And last night when I set it off to Jim about midnight, I didn't get the updated one. So,
Okay, but those 4 angles are the answers to 4
all of your questions,
this
all your
exam?
questions. Yeah, all your questions. You're going to have, they used to have almost 20 of those questions in here. And now I think they're down to about 12 in here.
Okay, but just those 4 angles.
Just those 4 angles. That's
Great.
correct.
All right.
Yeah. Now it may be 100, it may be 1,000, but it's still going to be just those 4 angles.
Right. I was wondering how, like, you were so able to say, oh, 1 kiloohm, 14 degrees, huh?
I've taught this thing since 2012, I think it is.
Yeah.
So, yeah, and some years I've taught 2 classes.
So I grab the different steps. So here's the actual steps to do the math. Use the rules 1 and 4 to add the resistance and reactances together. So the Z equals 1000 plus J250 minus J500 gives you the 1000 minus J250, and then convert Z into the polar form using the formula R. The square root of 1000 squared plus the negative 250 squared equals 1031. So the degrees tangent of negative 250 divided by 1000 equals 14 degrees, and the Z, so the Z would be 1031 with an angle of negative 14 ohms on page 422. And boy, that was fun cutting and pasting that bad boy into the slide deck.
Yeah, that math can give you headaches too. So sometimes you just memorize it a little bit, it will be okay.
Yeah, that's definitely a memorization one, because that math is way back in the 70s for me. Except now. Okay. So the correct answer was Charlie, 14 degrees with the voltage lagging the current. What is the phase angle between the voltage across and the current through a series RLC circuit if XC equals 100 ohms, R equals 100 ohms, and XL equals 75 ohms? A, 14 degrees with the voltage lagging the current. B, 14 degrees with the voltage leading the current. C, 76 degrees with the voltage leading the current. Or D, 76 degrees with the voltage lagging the current.
A.
This one is alpha, and there is the big long steps, or you can grab the answer from Daniel's sheet, which I can jump back or send that out later. What is the phase angle between the voltage across and the current through a series RLC circuit if XC equals 25 ohms, R is 100 ohms, and XL is 50 ohms? A, 14 degrees with the voltage leading current, 14 degrees with the voltage leading the current. C, 76 degrees with the voltage lagging the current. Or D, 76 degrees with the voltage leading the current.
B.
Baker is the correct. 14 degrees with the voltage leading the current. Lots of fun steps there. What is admittance? A, the inverse of impedance. B, the term for the gain of a field effect transistor. C, the turns ratio of a transformer. Or D, the inverse of Q factor. Correct answer is it's the inverse of the impedance. That's what admittance is. Hang on real quick, I just saw another. Okay. Never mind, this is something else. I thought it was another person joining the wrong room. Okay. Which point in figure E5-1 best represents the impedance of a series circuit consisting of 400 ohm resistor and a 38 picofarad capacitor at 14 megahertz? And you can't see the point because I have it on the next slide. I should have put it in here. Point number 2, point number 4, or point number 5, point number 6. And there's the actual answer and the figure. So the first step is to calculate the capacitor's reactance, and then use the rule number 1 to add the resistance and the reactance together, and then locate the point on the graph. And the correct answer is 4, letter B. And my mouse isn't working. There it is.
Move your cursor on point 4. It's hard to see.
Yeah, hang on.
There it is in the bottom.
Yep, it's right here. Okay.
You know it's going to be on a 400 line because that's purely resistive.
Yep. So your pure resistance is this line here. So like Mark said, you know it's going to be one of these points, and then you just have to add in the math and find that negative 300, which would be, oh, mouse, there it is. There's your negative 300.
Or because it's a capacitive reactance, you know it's in the negative.
Yeah.
That gives you 1 point.
Yep, that gives you the other clue.
Sage math.
Okay, let me move this over some more so I can see the next screen. Which point in figure E5-1 best represents the impedance of a series circuit consisting of a 300 ohm resistor and an 18 microhenry inductor at 3.505 megahertz? So we know that it's going to be 300 ohms resistance, so we're going to go over to the right to the 300 ohm mark, and since it's inductance, we're going to go up. Let me move this once again. So here's the math for it. We're going to calculate the inductor's reactance using X of L equals 2PFL, and you'll get 400 ohms. And then use rule 1 to add the resistance and the reactance together. So you're going to have a Z of 300 plus J 400, and then locate on the graph. So you go over 300 and then up. So the up to the 400. So your point is
Oh.
point number 3. Let me move this way over that way. Okay. Which point on figure E5-1 best represents the impedance of a series circuit consisting of a 300 ohm resistor and a 19 picofarad capacitor at 21.200 megahertz? So again, we're going to go over to the right on the 300 ohm area, and since it's a capacitor, it's going to be in the lower part. So calculate the capacitor's reactance. X of C equals 1 over 2 of C, get a negative 400 ohms. Use the rule 1 to add the resistance and reactance together. You get a Z of 300 minus J 400. So we go over to the 300. Wow, that is really small. And then the negative 400, come on mouse, is down here, is point number 1. I need to edit these slides and put the figure E5-1 in the question part so you can see it. Okay, reactive power and power factor. We have 10 questions in this one. Let me move this over. What is the power factor of an RL circuit having a 30-degree phase angle between the voltage and the current? A, 1.73, B, 0.5 or 0.5, C, 0.866, D, 0.577.
C.
Charlie is correct. It is the cosine, power factor is the cosine of the phase angle. So cosine of 30 is 0.866. Move that a little bit more.
This ought to bring everybody back to their trig days.
Yeah, 1978
Because
was
it's the
this stuff.
opposite side.
Yep.
Yeah, I think the answer would be E on this one. Memorize.
Oh yeah, okay. Whee! That one went right over my head. Boy, did you get me. I was going, what? Yeah, E, memorize. Okay. Wow. That was good. Okay. How many watts are consumed in a circuit having a power factor of 0.71 if the apparent power is 500 volt amps? A, 704 watts, B, 355 watts, C, 252 watts, or D, 1.42 milliwatts.
E.
Bravo.
Bravo is
Yeah.
correct. Use the equation 4.11 to find the power factor real. So you have a power factor real versus apparent. 500 times 0.071 is 355 watts. How many watts are consumed in a circuit having a power factor of 0.6 if the input is 500 volts AC at 5 amperes? A, 200 watts, B, 1000 watts, C, 1600 watts, or D, 600 watts?
E.
Delta is correct. And using formula or the equation 4.7, power apparent is I times E, 5 amps times 200 volts is 1,000 volt amps. Then multiply the power factor as in equation that's covered up by my other screen, 4.1. Power real equals power apparent times power factor. 1,000 times 0.06 is 600 watts. What happens to reactive power in an AC circuit that has both ideal inductors and ideal capacitors? Note ideal inductors and ideal capacitors. A, it is dissipated as heat in a circuit. B, it is repeatedly exchanged between the associated magnetic and electric fields, but is not dissipated. C, it is dissipated as kinetic energy in a circuit. D, it is dissipated in the form of inductive and capacitive fields.
Delta.
B.
Baker is correct. And this is with ideal inductors and ideal capacitors. So it would just sit there and exchange itself back and forth and it wouldn't dissipate anything.
Can I ask a quick question, Jim? I don't mean to be difficult.
No.
But on page 424, I'm looking here at the actual question, and I'm trying to look in that paragraph for that wording, and I just can't see it. Am I just missing it, or maybe somebody else can see it, but I don't see where that is. Or Bravo repeatedly exchanged between associated magnetic and electric fields is not dissipated.
In the first full paragraph at the top of the page.
Okay. Usually the answer is in the second paragraph closest to the answer. I get it now. Thank you. Sorry, I appreciate it.
Where did you find it again? Oh yeah, right at the very top.
Right.
Paragraph.
Yep. So it says a perfect capacitor or inductor does not dissipate or consume energy, but current does flow in the circuit when the voltage is applied to it.
Right.
Yep. So it's at the very top.
Yes. Thank you. That's just confusing. Should have been closer to the question.
Yeah.
I appreciate it. Thank you, guys.
Yeah. Usually it is close to where they mark the actual question.
Thanks again.
Okay, hang on real quick. Got somebody texting me. Okay, family stuff. Never mind. Okay.
That one was clear on the Castler video, the way he showed it. That was a good explanation.
Yeah, and the key thing on this one is I'm picking up on it when it says ideal inductors and ideal capacitors. How can true power be determined in an AC circuit where the voltage and current are out of phase? A, by multiplying the apparent power by the power factor. B, by dividing the reactive power by the power factor. C, by dividing the apparent power by the power factor. Or D, by multiplying the reactive power by the power factor. When voltage alpha is correct, when the voltage and current are out of phase, you multiply the apparent power by the power factor. What is the power factor of an RL circuit having a 60-degree phase angle between the voltage and the current? A, 1.414, B, 0.866, C, 0.5, or D, 1.73.
Charlie.
Charlie is correct. The power factor for a phase angle of 60 degrees is the cosine of 60, which is equal to 0.5. How many watts are consumed in a circuit having a power factor of 0.2 if the input is 100 volts AC at 4 amperes? A, 400 watts, B, 80 watts, C, 2000 watts, or D, 500 watts?
B. B.
Bravo is correct, and we're using equation 4.7. Let me move this over so I can read everything. Start by using apparent power using equation 4.7. Apparent power equals 100 volts times 4 amps equals 400 volt amps. Real power is then found by using equation 411. Power real equals 400 volt amps times 0.2 equals 80 watts. How many watts are consumed in a circuit consisting of a 100 ohm resistor in series with a 100 ohm inductive reactance drawing 1 ampere? A, 70.7 watts, B, 100 watts, C, 141.4 watts, or D, 200 watts?
Bravo.
B, Bravo.
Bravo is correct because this is only the resistance consumes power. The power real equals I squared times R, so 1 amp squared times 100 ohms gives you 100 watts. What is reactive power? A, wattless, non-productive power. B, power consumed in a wire resistor in an inductor. C, power lost because of leakage or capacitor leakage. D, power consumed in a circuit Q.
A.
Alpha.
Alpha is correct. Wattless, non-productive power. What is the power factor of an RL circuit having a 45-degree phase angle between the voltage and the current? A, 0.866, B, 1.0, C, 0.5, or D, 0.707?
D.
D is correct. Delta power factor for a phase angle of 45 degrees is the cosine of that 45, which gives you the 0.707. Whew. Resonant circuits, 9 questions. What can cause the voltage across reactances in a series RLC circuit to be higher than the voltage applied to the entire circuit? A, resonance, B, capacitance, C, conductance, or D, resistance?
A.
Yeah,
Alpha.
Alpha. At resonance, you're going to get higher voltage than the entire circuit. What is resonance in an LC or an RLC circuit? A, the highest frequency that will pass current. B, the lowest frequency that will pass current. Or C, the frequency at which the capacitive reactance equals the inductive reactance. Or D, the frequency at which the reactive impedance.
It's 8 o'clock.
Yes, it
Well,
is.
thank you, Mr. Time and Temperature Disc Jockey.
Last answer is D, the frequency at which the reactive impedance equals the resistive impedance. So what is the resonance? Charlie is the correct answer in this one. The frequency at which the capacitive reactance equals the inductive reactance.
That was that chart on page, the figure 424 on page 427. That was what I remembered. That chart.
On 427.
Page 427, figure 424.
Oh, yeah. Yep. Yep. Kind of, sort of. Yep.
Kind of, sort of, maybe.
Yeah, it's there. It's just I can't I can't screenshot it very easily. Okay. All right. What is the magnitude of the impedance of a series RLC circuit at resonance? A, high as compared to the circuit resistance. B, approximately equal to the capacitive reactance. C, approximately equal to the inductive reactance. Or D, approximately equal to the circuit resistance.
Hey, delta.
Delta is correct. It's approximately equal to the circuit resistance when it's at resonance. What is the magnitude of the impedance of a parallel RLC circuit at resonance? A, approximately equal to the circuit resistance. B, approximately equal to the inductive reactance. C, low compared to the circuit resistance. Or D, high compared to the circuit resistance.
Alpha.
Alpha is the correct answer. It's approximately equal to the circuit resistance. What is the magnitude of the circulating current within the components of a parallel LC circuit at resonance? A, it is at a minimum. B, it is at a maximum. C, it equals 1 divided by the quantity 2 times pi multiplied by the square root of the inductance L multiplied by the capacitance C. Or D, it equals 2 multiplied by pi multiplied by the frequency F multiplied by the inductance L.
Bravo.
Bravo is correct. It's at a maximum when it's at resonance. What is the magnitude of the current at the input of a parallel RLC circuit at resonance? A, minimum. B, maximum. C, R divided by L. Or D, L divided by R.
Well, you old timers ought to be able to figure that one out, how we used to tune the thing.
Yeah, alpha. Yeah.
Dip. You're looking for the dip in your grid dip. What is the phase relationship between the current through and the voltage across a series resonant circuit at resonance? A, the voltage leads the current by 90 degrees. B, the current leads the voltage by 90 degrees. C, the voltage and current are in phase. D, the voltage and current are out of phase.
Charlie.
Charlie is the correct answer. The voltage and current are in phase. What is the resonant frequency of an RLC circuit if R is 22 ohms, L is 50 microhenries, and C is 40 picofarads? A, 44.72 megahertz, B, 22.36 megahertz, C, 3.56 megahertz, or D, 1.78 megahertz?
C.
Charlie.
Charlie is correct. And the biggest stumbling block per the book is remembering to convert the inductor values to henries and the capacitor values to farads, and then you can use the equation to calculate. And there's all of the heavy duty math from 1978. Yeah, roughly.
1960. Come on.
Okay, 1960 was when I was born. What is the resonant frequency of an RLC circuit if R is 33 ohms, L is 50 microhenries, and C is 10 picofarads? A, 23.5 megahertz, B, 23.5 kilohertz, C, 7.12 kilohertz, or D, 7.12 megahertz?
Delta.
Delta is correct. And there's the math for that one. Queue of components and circuits. 8 questions on this one. Which of the following can be used to measure the Q of a series tuned circuit? A, the inductance to capacitance ratio, B, the frequency shift, C, the bandwidth of the circuit's frequency response, or D, the resonant frequency of the circuit? Charlie is correct. It's the bandwidth of the circuit's frequency response. What is the result of increasing the Q of an impedance matching circuit? A, matching bandwidth is decreased. B, matching bandwidth is increased. C, matching range is increased. Or D, it has no effect on impedance matching?
A.
A is correct. The matching bandwidth is decreased. How is the Q of an RLC parallel resonant circuit calculated? A, reactance is either the inductance or capacitance divided by the resistance. B, reactance of either the inductance or capacitance multiplied by the resistance. C, resistance divided by the reactance of either the inductance or capacitance. Or D, reactance of the inductance multiplied by the reactance of the capacitance. That was a long one. Correct answer is C, the resistance divided by the reactance of either the inductance or capacitance. How is the Q of an RLC series resonant circuit calculated? Wait a sec, did I just double
No.
Okay, there.
Uh,
Just
Same question, only different.
yeah, it's differently worded. Okay. How is the Q of an RLC resonant circuit calculated? A, reactance of either inductance or capacitance divided by the resistance. B, reactance of either the inductive or capacitance multiplied by the resistance. Or C, resistance divided by the reactance of either the inductance or capacitance. Or D, reactance of the inductance multiplied by the reactance of the capacitance.
With Charlie. A.
Alpha is the correct one on this one. The reactance of either the inductive or the capacitance divided by the resistance.
The difference in those two questions is just series and the other one parallel.
I didn't catch that, but yeah.
Yeah.
There you go. Parallel and series. I was scratching my head. Did I double copy this one right? Okay. What is the half power bandwidth of a resonant circuit that has a resonant frequency of 7.1 megahertz and a Q of 150? A, 157.8 hertz, B, 315.6 hertz, C, 47.3 kilohertz, or D, 23.67 kilohertz?
Charlie.
Charlie. 47.3.
Charlie is correct. And the delta frequency is frequency resonance over the Q, which gives you 47.3 kilohertz. What is the half power bandwidth of a resonant circuit that has a resonant frequency of 3.7 megahertz and a Q of 118? A, 436.6 kilohertz, B, 218.3 kilohertz, C, 31.4 kilohertz, or D, 15.7 kilohertz?
Charlie.
B.
Charlie is correct. Same frequency, delta frequency is frequency resonance over the Q. What is an effect of increasing the Q in a series resonant circuit? A, fewer components are needed for the same performance. B, parasitic effects are minimized. C, internal voltages increased. Or D, the phase shift can become uncontrolled.
C.
C is correct. The internal voltages increase.
All of these particular things you're looking at now is the math and physics behind why loop antennas work very efficiently, because the Q is just out of sight. Give Jim a chance to get his swig down there.
Yeah. Thanks, Mark. Which of the following increases Q for inductors and capacitors? A, lower losses. B, lower reactance. C, lower self-resonant frequency. Or D, higher self-resonant frequency?
Alpha.
Alpha.
Alpha is correct at lower losses. Components at RF and microwave frequencies. 9 questions. What is the result of skin effect? A, as frequency increases, RF current flows in the thinner layer of the conductor closer to the surface. B, as frequency decreases, RF current flows in a thinner layer of the conductor closer to the surface. C. Thermal effects on the surface of the conductor increases the impedance. Or D. Thermal effects on the surface of the conductor decrease the impedance. The correct answer is A. Skin effect is as the frequency increases, the RF current flows in the thinner layer of the conductor closest to the surface. Why is it important to keep lead lengths short for components used in circuits for VHF and above? A. To increase the thermal time constant. B. To avoid unwanted inductive reactance. C. To maintain component lifetime. Or D. All of these choices are correct.
Bravo.
I heard a bravo out there. To avoid unwanted inductive reactance. Why are short connections used in microwave frequencies? A. To increase neutralizing resistance. B. To reduce phase shift along the connection. C. To increase compensating capacitance. Or D. To reduce the noise figure.
Bravo.
Bravo is correct. To reduce the phase shift along the connection. What is the primary cause of inductor self-resonance? A. Inter-turn capacitance. B. The skin effect. C. Inductive kickback. Or D. Non-linear core hysteresis.
Alpha.
Alpha.
Alpha is correct. The inter-turn capacitance. Which of the following device packages is a through-hole type? A. The DIP. B. PLCC. C. Ball grid array. Or D. SOT.
Alpha.
Alpha.
Alpha is correct. A dual inline pins, is that right?
Yes.
DIP.
Do they give the definitions of the rest of those?
It's package, isn't it?
Yeah.
Dual inlet package.
Dual inline package, that's correct. Yep. And no, they don't give descriptions of the rest of those. Which of the following component packages would be the most suitable for use at frequencies above the HF range? A. A TO220. B. Axial lead. C. Radial lead. Or D. Surface mount.
D.
Delta.
Delta.
Delta is correct. Surface mount is better used for HF and above. What advantage does surface mount technology offer at RF compared to using through-hole components? A. Smaller circuit area. B. Shorter circuit board traces. C. Components have less parasitic inductance and capacitance. Or D. All of these choices are correct.
Delta.
Delta is correct. All of these are correct. What is the characteristics of a DIP packaging used for integrated circuits? A. Package mounts in a direct inverted position. B. Low leakage, doubly insulated package. C. 2 chips in a package, dual inline package. Or D. A total of 2 rows of connecting pins placed on opposite sides of the package, dual inline package.
Delta.
Delta.
Delta is correct. Why are dip through hole package ICs not typically used at UHF and higher frequencies? A, too many pins. B, epoxy coating is conductive above 300 megahertz. C, excessive lead length. Or D, unsuitable for combining analog and digital signals.
Charlie.
Charlie is correct. The excessive lead length. Magnetic cores. We're almost to the end. 10 questions. Why should core saturation of impedance matching transformer be avoided? A, harmonics and distortion could result. B, magnetic flux would increase with frequency. C, RF susceptance would increase. Or D, temporary changes of the core permeability could result.
Delta. Alpha.
Alpha is the correct answer on this one.
Wow.
Harmonics and distortion could result. Which materials are commonly used as a core in an inductor? A, polystyrene and polyethylene. B, ferrite and brass. C, Teflon and Delrin. D, cobalt and aluminum.
Bravo.
Bravo is correct. Ferrite and brass. What is one reason for using ferrite cores rather than powdered iron in an inductor? A, ferrite toroids generally have lower initial permeability. B, ferrite toroids generally have better temperature stability. C, ferrite toroids generally require fewer turns to produce a given inductance value. Or D, ferrite toroids are easier to use with surface mount technology.
Charlie?
Charlie is correct.
Better be Charlie.
Generally requires fewer turns for a given inductance because it keeps it all in there. Little sugar. What core material property determines the inductance of an inductor? A, thermal impedance. B, resistance. C, reactivity. Or D, permeability.
Delta.
Delta is correct, the permeability. What is current in the primary winding of a transformer called if no load is attached to the secondary? A, magnetizing current. B, direct current. C, excitation current. Or D, stabilizing current.
Alpha.
Alpha is correct, magnetizing current. What is one reason for using powdered iron cores rather than ferrite cores in an inductor? A, powdered iron cores generally have greater initial permeability. B, powdered iron cores generally maintain their characteristics at higher currents. C, powdered iron cores generally require fewer turns to produce a given inductance. Or D, powdered iron cores use smaller diameter wire for the same inductance.
Bravo.
Bravo is correct. Powdered iron cores maintain their characteristics at higher currents. Hang on a sec. Okie dokie. What devices are commonly used as VHF and UHF parasitic suppressors at the input and output terminals of a transistor HF amplifier? A. Electrolytic capacitors. B. Butterworth filters. C. Ferrite beads. Or D. Steel core toroids.
Charlie.
Charlie, yeah.
Charlie is correct. Ferrite beads. What is a primary advantage of using a toroidal core instead of a solenoidal core in an inductor? A. Toroidal cores confine most of the magnetic field within the core material. B. Toroidal cores make it easier to couple the magnetic energy into other components. C. Toroidal cores exhibit greater hysteresis. Or D. Toroidal cores have lower Q characteristics.
Alpha.
Alpha.
Alpha is correct. It confines most of the magnetic field within the core material.
Do they explain in there the difference between both types? What's the difference between a toroid and a solenoid core?
Yeah, toroid is the little circle donut, and the solenoid has, like a solenoid, has a circular coil. Yeah.
Okay. If they explained it, then it's easy to understand.
4-36.
I wasn't sure if there was anything such called a solenoidal or
solenoidal core. Yep.
Yeah, I can't even say it.
Yep. It's on page 436 down at the bottom. Core-shaped toroids. Okay. Which type of core material decreases inductance when inserted into a coil? A. Ceramic. B. Brass. C. Ferrite. Or D. Powdered iron.
Bravo.
Bravo is correct. Brass reduces inductance. What is inductor saturation? A. The inductor windings are overcoupled. B. The inductor's voltage rating is exceeded, causing a flashover. C. The ability of the inductor's core to store magnetic energy has been exceeded. Or D. Adjacent inductors become overcoupled. Charlie is correct. The ability of the inductor's core to store magnetic energy has been exceeded. Dib, 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 dib. That's all, folks. Made it.
Thanks, Jim.
Thank you.
Yeah.
Wow. That was great.
That was a long, long road.
Hey, it's Daniel.
We got a half hour left.
You got a half hour left.
We can go work some more equations.
You can do the math.
Yeah.
Well, I also have the class tonight, so I was going to do the class last 7. So
Mute Daniel so we don't listen to his phone call. Oh, goodness.
Back on that.
Could somebody talk a little bit more about the Eli the Iceman rule? I forgot about that.
Yeah, so Eli, E is voltage, L is inductance, and I is current. So in an inductor, in an inductive circuit, L, the voltage leads the current. And in a conductive, the ice one, I is the current, C is the capacitance, and E is the voltage. So in a
It's
capacitive, it's 8:30. in ice, the inductance in a the current leads the capacitance.
No, leads the voltage.
The capacitor,
Voltage.
yeah, it's been a long night.
You have to visualize. You got to draw it out with the E, the L, and the I. So if the E is in front of the L, then it's voltage leading in an inductive circuit.
Yeah. Let me find that page because there is a couple of diagrams in there.
I don't think the book identifies it as either Eli or ICE. Other sources do.
Mm-hmm.
Yeah, I actually did find it.
Eli the Iceman in the book?
Yeah, Eli the Iceman was listed. It's on page 4-15.
Oh, okay.
And it is in the second paragraph.
Yeah.
And it says a useful mnemonic for remembering relationships is Eli the Iceman. The L and C represent the inductor and capacitor, and the E and I stand for voltage and current. Right away you can see that E, voltage, comes before or it leads I, the current, in an inductor, and that I comes before or that leads E in the capacitor. Using the same convention for the capacitor, the phase angle in an inductor is 90 degrees positive. Eli the Iceman, that was one that I remembered.
Thanks.
Yeah, this is Daniel again.
Well, go ahead, Dan.
Yeah, I had a real live experience with Eli, the Iceman. I was measuring the voltage on a power transformer in a Bogen audio amp, and it's supposed to have been 490 volts. Well, I said, lift the lead, and it threw me against the wall. When you change the current on a transformer, it will spike. And that spike is in voltage, and it threw me against the wall. I seen the meter jump off to the 1500 volt side and bounce off. I looked over to see why my partner hit me. He looked over to see why I jumped. But if you change current on a transformer, just a little bit of current that goes through a voltmeter, and those plastic things on the leads are not enough. They say 600 volts or 1000 volts. It's not enough. You will get thrown against the wall. I was still about 18 or so, 17, 18 when that happened. I go, whoa.
Wow.
Transformers will spike the voltage when they're a little bit of current is changing. So that's yeah. And it's a capacitor is like filling a swimming pool. You put a lot of water in real fast, then you slow it down so you don't overfill the swimming pool. That's what I think about a capacitor, taking a lot of current, a lot of water to fill the pool up. But when you're getting toward the top, you want to back it off and slow the water back so you don't dump as much water in. So that's my 2 cents.
Cool, thanks.
We
Daniel.
talk about, maybe not yet. Did we talk time constants in any of this reading so far? I might have missed some of it.
Yeah, that was the very first question, actually, I think.
Yep.
The very first section. With time constants.
Time constants are right at the very beginning.
That's why I missed it, because I was a little slow getting here tonight.
Yeah, pages 4-8 starts the time constants.
Thank you. It's just too many meetings.
Room is zoom.
Going back to that question about Eli, the Iceman, and whether you're going to memorize things or whether you're going to understand it, I keep in mind the fact that when you think about a capacitor, you know that the current is flowing into the capacitor, and the voltage rises until to a certain maximum point for the capacitor. And then when you think about an inductor, you know that the voltage is entering the inductor and it's raising the current up to a certain point, or actually the back current, if you want. That, so it's like, if you keep that in mind, that's like more of an understanding of Eli the Iceman. But if you're going into the test and you want to pass the test, it's like Eli the Iceman.
Yep.
Will do it for you.
Yep. And all of these little things, your mnemonics and your formulas, bubble them into the brain, and then as soon as you sit down and they say, okay, you can use your scratch paper before you even start answering questions, take that minute to do that brain dump and write all of that stuff down on that blank sheet of paper. Because when you get in and you open up the test questions, you're immediately, okay, I got to solve this. And if you take just, 5 minutes, 2 or 3 minutes and write all your formulas down on that scratch paper, you won't get all twisted around. You'll have everything fresh and, written out for you. That was the first thing that I did on all of my tests, is I did that brain dump onto that scratch paper. That way I had all those formulas and I didn't get twisted up by, getting those distractors, and I go, oh, well, maybe that was the right answer. Nope, there it is, Eli the Iceman. Look at that. Or the little pie chart with the P over I and E. I always wrote, even if it was simple stuff, I would write it all down so I wouldn't get my brain off on a distractor and go, well, maybe I didn't remember that right.
Yeah, I was talking to Jim last night about what we're trying to do is de-stress you for the test. You have enough stress already striving for the extra test. So what we're trying to do is give you as much as we can, so that when you look at a question, you have two ways to look at it, and you have more confidence in that question and can put your mental energy to the next question you're not quite sure of. So we're trying to de-stress you guys going into this test.
Yeah, and since this is all new to me, that's why I'm glad Daniel is here, because he's taught classes for many, many years compared to my first time at playing craziness. And hey, Daniel, I didn't have any mess ups in my charts
PowerPoint.
Tonight, my PowerPoints.
What I did is, what happened, I had both my brothers call me after we got off class last night. And so then I worked on that PowerPoint, and I must not have saved it before I sent it to you, because I got to close it. So I must have forgot to save it.
Yeah.
That's why we had some things in there. So we'll get back to it tonight and get it taken care of. We'll get it sent out.
Cool. And again, I'm recording all of these, and I'll send the email out tomorrow with the recording link for those that were late. Yeah, Joe?
Another thing about test taking that I have found has been real helpful for me is that as you're taking the test and you come upon a question that you don't immediately know the answer to, and you know it's going to take you some time to figure it out, go by it.
Yep.
And go on to the other questions that you can answer. Yep. And a lot of time, as you go through the other questions, that answer will pop up to that question, or it'll shorten.
Yep.
So, and you'll be able to go over many more questions than if you get hung up on one question, like, oh, how am I going to figure this out, and and spend all that time, and then the next thing you know is, well, the time is really up on this session.
Yeah, yeah, very true. And again, there's 50 questions, and you need 37. Is that right,
Yes.
Daniel?
Yes. Yes.
So yeah, you can completely blow off 13 questions and pass the test like I did, but then you'll want to go back and understand what the heck did I. But it's a binary. You'll pass or fail, one of the two. So maybe it's better to just say, did I pass or did I fail, and then go with that. But yeah, I did do the ones that just pop out at you, just hit them right away. And if you're gonna have to spend a lot of time, figuring out the math or whatever, or you haven't memorized that particular one, just move on and keep going, and then go back later after you've gone through that initial first run.
Yeah.
That's a real good tip.
The other thing, we had a gal pass a tech in general and go for the extra. And if she had a question she didn't know, she chose the longest answer. And
Yeah.
she got like 29 or 30 of them right. She always chose the longest answer. So look at the longest answer, and you'll probably is right.
Yep.
Did you say the lowest or the longest?
Longest.
Longest. One that has the most words in it.
Actual results may vary, but yes.
Yeah, I would say so.
So on the test, we'll be able to go back to previous questions.
Yeah, you're gonna be given. You'll be given a document, and you can just go through the document. You can jump around. You can say, oh well, that one's too hard. Let me jump to the next one.
All right, so it's not an electronic test; it's a paper test.
Oh no.
But Zoom class is going to be electronic test.
Yes, sorry. Yep.
So will we be able to go back to previous questions?
If you're in person, and I'm just on the, I got a call from Dean Kushner, one of my instructors, and we're going to try to have a in-person test in March for you guys. So you have an option, either do the Zoom or the in-person test.
That'd be good.
So we're setting that up because we got
I like in person myself.
Yeah.
Yeah, that's fine. My question though is, if it's an electronic test, can we go back to previous questions and check on them?
I'm going to make the assumption, yes, you can bounce around, but I'm not 100% sure because this is kind of new for everybody here. I'd have to double check with Scott and see how that works.
Yeah, I don't know. On many of them, I've taken some hamstudy.org. I think you could go back and review different questions on the thing, and I'll have to ask her that. I don't know.
Yeah,
I've helped out with the online, the parking lot test.
And like, in addition to whether you can go back and forth and check on them, if you can, is there a way on the electronic tests of marking the ones that you're passing, that you're, like you're going on from those that you haven't answered that, so that you don't mess up your answers, where like you didn't answer number 19, and then in number 19 answer, you put in the answer for 20, and you're going to be completely messed.
Yeah. You see, if you had a paper test like that, we as the VEs have the authority to move the template up and say, hey, he's got everything else lines up. He just got a one off, and then give you credit for the test. But on the electronic test, I'm not sure. That's why you have a scratch paper there and write the numbers down that you're missing.
Yeah.
So
yeah,
I'm gonna get out of here. I got some guy waiting for me. So
okay. Thanks, Daniel.
Thank you.
Yeah, so that's the technique that I did too, is like Daniel said, if you're doing on your scratch paper, if you didn't pick up on question 20, you write 20 down so that you can go back and review it at the end. So yeah, but as far as how we're doing the electronic, I need to double check with Scott and see if you can bounce around, because I've been in couple of different test things online, and some of them you could, mark with a little red marker to go back and review it afterwards. And others, it kind of went in sequence, and there was like you answered and there was no going back. So have to double check and find out from Scott how that is. One thing I would suggest is going to the ARRL, and there's the sample tests that you can join there, and then the ham study is that's the other group to look at their sample test questions or do those. Couple of online places. I'll add that into the email, the test review site, so that you can start looking at it, because we're at that point to where you can study and start doing some of the test questions. I like the ARRL one because that one specifically had a make up a bunch of tests based on the chapter in the book versus the entire question pool. So I've been kind of doing that. I've done that a couple of times where I'm studying just that particular chapter. But I do like the ham study. I use them both, but actual results may vary, as people say. Any other questions or thoughts, comments before I stop the recording?
Well, also like talking about the ARRL test questions, I found in studying for the general that what I would do is I would take it section by section, but I would always make note of the questions that I missed.
Yeah.
And then that would form a smaller subset of questions or topics that I had to focus on.
Yep.
Yep. That's one way of reducing your like attention demanding load.
Yep. Okay, let me stop the recording.